is also given over here. You can look at that. There is only, I have made provision of loading only one PDF report. So in that PDF report, you can report the delay computation of ripple carry adder subtractor and also just the ripple carry adder. Okay. You can report both in the same PDF file. Now regarding your login, so when you want to submit the assignment, you click on students. Okay, click on students and then click on assignments. So you will be prompted for a login. That is where you should provide your username and password. If you try to log in from other places, I mean, you will also, for example, if you visit the submission log, so you might click somewhere here, but it will not work because here it is for course management evaluation, whereas for the other case, for students, it was well, it is already showing unauthorized. Anyway, so last time, so it was a different authentication domain. So yeah, so you have to access it from this place, students, then assignments. That is you'll have to access it from there. All right, okay. So, and those of you who haven't yet, I mean, yeah, so there is one submission for per group. Just note that as of now, you should submit all the files together. If you, for example, if you have submitted, say, if you submit one file now and you try to submit the remaining files later, then the file that is currently submitted will be lost. That is the present situation. We might try to change that, but as of now, that is the way it is. So submit all your files together. Yeah, just remember to do that. Okay.
Sir, for even now, we will submit group wise.
Yes.
The first assignment.
Yeah, any member of the group can submit. That will be fine. But just remember to submit all the files together. Yes. Because any earlier submission, any file submitted earlier will be lost. Basically will be deleted. So submit all your files together. Okay. So let us look at this. Yeah, so last time we saw how this double algorithm is working. So let us just see if we can reason something about its correctness. So what we are trying to do is we are trying to convert a binary number to a binary coded decimal number. So we let's say we follow This is your binary number. This is a binary number of n bits, and this is your binary coded decimal number in m digits. All right. So as you can see that this algorithm involves shifting a bit in at every step. So the value of the DJ can be the BCD number after the jth shift. So D0 is the initial number, which is all zero. Okay. So initially, as you have seen, you have all zero. You can just keep that also open side by side. Yeah. Rather, I'll open it in this. All right. So yeah. So initially it's all zero. So this is actually what you're seeing here. This is actually D1. Alright. So D0 is all zeros. That is actually not shown over here. D0 is all zeros. This is D0. Alright. Just making it a little smaller. Alright. Okay. So now, um, so yeah, so initially each BCD value yi. So let us say that um, the value of digit di, I just called it yi. Maybe I could have called it di. Anyway, so initially each BCD value yi of digit di is valid. It is 0. All right. Now we assume that at least one bit is pending conversion initially. All right. So on a left shift, each new BCD value has, I mean, that's how you have the value updated. All right. So it is 2yi. So this is, say, a digit. This is di. All right. I mean, this is di. So if you look at this, what is happening is that the value is getting updated as follows. So this is, say, this one is, of course, D0. So what you see here is, say, for example, y0, or maybe I can just open a new instance. Yeah. So here, what you see is, say, D0. D0 was I'm saying for, for D0, D0 was all zeros, right? As you can see, you have got all zeros, all right? And what is, so, so after your first shift, what you have is D1 really. So what is D0 dash? That is 2 times, because you are doing a left shift, 2 times D0 uh, plus, one second, yeah, plus this bit really. It is this bit which is coming in here. This is the bit which is coming here, all right? So plus uh, so over here what you're saying is that, so in this case, for this example, it is 1, all right? Or as such we are calling it, we are calling it, so the value, uh, or if we just call it, so this is where, according to what is written here, this is y0, so maybe we can just call it y0 dash. We will follow this convention. So this is also, so y0 dash is 2 y0 plus mi minus 1. So mi minus 1 is, so mi minus 1, so you will have the situation. So we are looking at, this bit or this bit or this bit and so on. So depending on, which DI you are considering. So that is the bit which comes in here, all right. That is the bit which comes in here. And this is the situation. Yeah, yeah. So that is what is happening. So this is how the value is getting updated. So this is what is written here. This is yi dash equals 2yi because of the left shift plus mi minus 1. That is the most significant bit. Most significant bit of d I minus 1, okay, or the next input bit. the, for this is the next input bit for for D0. Alright, that is for D0 it is the next input bit, as you can see. So this is what is happening. Alright. Now and you find that this relationship holds for D1. So for D1 this is exactly what is happening. If you see for D1 this is exactly what is happening. So this is D1, this is D2, this is D3. Alright. For D1, D2, D3 this is what goes on, because the maximum value that you can have. So what is the maximum value of D1? Maximum value of D1, so you can say max for D1 is equal to 1, D2 is equal to 3, and D3 is equal to 7. Sorry, D3 is 7. Alright, so these are the maximum values. Now, this one of course is greater than or equal to 5. But for D1, D2, D3, these relationships hold, as you can see. So D1, for D1 you are taking in B15, for D2 you are taking in B12, and for D3 you are taking in. So that is what is happening. You are taking in, this is in, I don't know how many bits are here. 1, 2, 3, 4, 5, 6, 7, 8. So in this case, yeah, so you have 16 bits. So this is B0, you can say. This is B0 and this is B15. So in this case, you do have 16 bits. Alright. You have 16 bits over here. Alright. So that is what is happening. Okay. B15, B14, B13 for this example, if you are working with 16 bits. Now what happens next? So thereafter there is always the possibility of some, so later on. So what happens next? Well, after shifting, as we saw yesterday also, after shifting, if your bits are exhausted, then your conversion terminates. And if they happen to exhaust after shifting the first 3 bits, then as you can see, the conversion is correct. If the conversion happens to terminate after shifting in the first 3 bits. Let us see what happens if you carry on. Alright. So if you carry on, what you check is that if the new value is greater than 5, then it gets updated, alright, because you're going to add 3, alright. So you have seen that that's exactly what you do. If the new value is greater than or equal to 5, as in this case, you update it. So the updated value is this, the updated value. Alright, you can say this is the, after adjustment, after you can say adjustment. After adjusting, this is the new value. Okay, so this is the new value after adjusting. All right. Now what happens is, after you have added this, of course, there will always be, this bit will always be 1. That is the whole idea of this adjustment, because, 5 or more means this bit will always be 1. All right. So this is really the next significant bit of B1 that will, so it will become the next significant bit of the higher digit after shifting. All right. So MSB, so that's why MSB of DJ is the carry to be shifted into DJ plus 1. That is what is going to happen. All right. So that will be shifted in, and on the next left shift, so this relationship holds again. That is, DJ is again 2dj minus 1 plus bn minus j because of this correction. So let us see if that holds over here. So what is this value? This value is 5, right? So let us write it here. That so here you can see, in this case, D3 is equal to, D3 is equal to 5. All right. D3 is equal to 5. So y dash is equal to 5 plus 3, which is 8. As you can see, this value is 8. And then you are shifting in. So when you shift it, so you are shifting, and in this case you are also adding 1. So that is 2 times 8 plus 1, that is 17. So that is actually what you have over here. 2 times 8. So 1 second. This is oh no, sorry, it is 2 times 5, not 2 times 8. So it is 2 times 5 plus 1, that is 11. So that is exactly what you have over here. Okay, this is exactly what you have over here. So this relationship holds again. So this happens for all the digits. This happens for all the digits. So what do we ensure is that with each left shift, we are ensuring that this invariant holds. That is, dj equals to dj minus 1 plus bn minus n minus j. This is actually just the appropriate bit which is coming in. Okay, this is the appropriate input bit which is coming in. So that is how you can see that this algorithm actually works correctly. All right.
So,
Yeah.
so which line does that 11 correspond to?
Sorry? Oh, 11. 11 is here. This is 11. This is 11. 1, 1. 11. Yeah. That is D4.
That
D4
is how it's interpreted.
Yeah.
Means
D4
it
is
is interpreted separately.
Yeah, that is how you interpret the value of binary coded.
Okay.
That is the value of this BCD numbers, isn't it? That is the interpretation, because here the base is 10. So the base is, this is 10 to the power 0, 10 to the power 1, and so on. This is binary coded decimal. But what is happening is, you are so if you look at this, uh, uh, if you look at this relationship is holding. Okay, so here it was 5. So now the value has become, the value is 2 times 5 plus 11. So the value is 11. All right, the value is 11, and that is what you're seeing. The value is 11. All right. So that is what you are getting through this operation of shifting. All right. Because these digits, when these are left shifted, the value gets doubled. So if you left shift this is 1, this becomes 2. So that is why that is why you have this relation. Okay, with each left shift, the value of the digit doubles, and in case the value turns out to be greater than or equal to 5, then you apply the correction. Okay, then you apply the correction. So that is how you find that this conversion is working. And the other interesting aspect of this conversion is that it is reversible. Okay, so just as you can convert from binary to BCD, if you just reverse the process, then you can convert from BCD to binary also. So that is so if you just carry out this same process in the opposite direction, you will get back the binary from the BCD. So we'll show that example also. So this is of course the example that you saw last time. So we'll just see how the process. Okay, let us show it here. So we'll just show how this process can be reversed. So let us consider this input. So this is actually the same input that we had over here after conversion. Okay, we are just starting with the same value that we had after conversion. This is the value that we had after conversion. We are starting with the same input. Okay, that is after conversion. So now instead of shifting left, we are going to shift right. All right, we are going to shift right, and so in the previous case we were adding 3. So in this case we'll be subtracting 3. All right, we'll be subtracting 3. So this is the value that we had. So now what we shall do is, whenever the value is greater than or equal to 10, because what you had is whenever the value was greater than or equal to 5, you added 3. You add, sorry, not 10, but greater than or equal to 8. So whenever the value is greater than or equal to 8, you are going to subtract 3. So you subtract 3, and then you just carry on this process. So it is just the reverse process. So you can just look at the steps. So here we are subtracting it, then again we do a right shift, and whenever the value is greater than or equal to 8, we'll do a subtract. So this is what is going on. So just follow the steps.
Excuse me, sir.
Yeah.
Sir,
Yeah.
when we started initially in the input, in the B3 was 8. So will we not first subtract 3 from there before doing the right shift?
Yeah, just a minute. So why didn't we do it? 1 second. One second. So, when are we doing the subtraction? Let me just see. So, mm, I think I think we should do that after the first right shift. Let us just see, because this is the input. I think after the first right shift we should do that. Yeah, after the first right shift. So just check. I think we have to do a right shift first, and after that we have to carry on with the conversion.
So isn't that like you said, it is exactly the reverse of the decimal to BCD conversion,
Yeah,
isn't
so
it?
yeah, so what we are doing
So
is, because what we do is, when we terminate, if you have, so if you remember, if you look at this, here we did not add because
no,
it
sir.
terminated here. So here we did not add 3. All right.
Exactly.
Yeah. So I think, yeah.
So yeah, I
Okay,
think
sir.
it is that is the I think that
Yeah.
is the reason why.
So yeah, so just look at it a bit carefully. Yeah. So I think, yeah. So if you just follow the steps, yeah. So in this case again we carried out a subtraction, and then we'll do a right shift. So here we did as you can see, here we did a subtraction. This is 8. Yeah. Here again it is 8. Okay. So here we did a subtraction. Yeah. Yeah, so now, I mean, you can, I think this is the, so why don't you just do the next step yourself? So maybe you can just try it out yourself. So here we are going to, we have done a subtraction, so then again you will do a right shift. So why didn't you just do the next step yourself? Just see what you get. One or two steps you can just do. So just try out the next step yourself. Yeah, so the bit in red is the first bit that was shifted out. Okay, the bit in red is the first bit that was shifted out. So all of these, so all these bits have resulted from the conversion. Yeah. So have you done the next step? Yeah.
Sir, in when we are doing decimal to BCD conversion, we first do the addition, then do the shift. So when we are doing BCD to binary, we do first the shift and then the subtraction, right?
Yeah, so that is what I did. So if you remember, as you can see
Yes.
over here, the first step is the right shift.
Yes, sir.
Yeah,
Oh,
first
right.
step is the right shift. Yeah. So over there also, what you are doing is, if you start off with all zeros, because D0 is all zeros. So after that so the first 3 steps involve just left shifting when you are converting from binary to BCD, because there is no correction to be made in the first 3 steps, or rather in the first 2 steps. After the third shift, you might have to correct if your value is greater than or equal to 5. All right. So yeah. So here also you first do a right shift and then you carry on. Yeah. So this is how it goes on, and yeah. So I think you should just try to work out 1 or 2 steps. Just try to work out 1 or 2 steps yourself.
Sir, when are we subtracting 3?
Whenever the value is greater than or equal to 8.
So like in the first, like in the previous slide, there was one step in which in the step 3, the value becomes 8 in B1. So
One
we are not
second.
subtracting 3 there.
Which one? Which one?
That in step
Here,
3.
this one. Are you referring to this one?
No, no, in step 3,
No.
B1.
So just I'll number. This is a. I'm just calling this big ones as steps. So you're talking about which one? You're talking about this three?
So second step.
This one, this step.
Yes, sir.
Yeah. So here, as you can see, uh, in these two cases, the value is greater than or equal to 8. So we are doing a subtraction. What
So
is your
like
problem?
sir, after subtracting 3 in column B1, the value becomes 8. So what are we like?
Oh yeah, that is all right. So what you are doing is you are carrying out the subtraction. You are carrying out the subtraction, and then you always do a right shift, and again you check. So after this, if it becomes yeah. So what you are seeing is that after this also the value is greater than or equal to 8. That is all right. So the way you do it is you always subtract and then you shift. Just so it is just the reverse of the previous case. So in the previous case, so in the earlier case, you would have had this situation. You would have basically first added 3 and then you shift left. So after you add 3, the value is actually greater than or equal to 5. After you add 3, the value continues to be greater than or equal to 5. So you shift left. Yeah. So this is all right. So here, if it is greater than or equal to 8, you do a subtraction and then you shift right. It is just the reverse of the previous algorithm.
Yes, sir. I understood.
Okay, so anyway, this is the conversion. So I think the final steps are involve mostly shifting. So as you can see, you get the same number that you started with here. You can. So it does work out. Yeah. And so I hope this process is okay. So now the next thing that we should consider is you have seen how it works, okay, but how can you implement it? How could you implement it? That is, of course, a challenge. So let us just consider this is, I'm just going back to the, yeah. So this is the yeah. So I'm just going back to this. So how can you implement it? We have seen how it works. So uh, one basic, thought that comes to us is, of course, if we could store this in, so you understand the concept of register because you have already studied that in your course on programming and data structures. You understand the concept of a register. So You could use the register, but right now we have not yet started with sequential circuits. So the question is, can you do it without a register? Is it possible to do it without a register? That means, could you think of a way to implement this using just combinational logic? Can you think of implementing it just using combinational logic? So, of course, this is a relatively big example. So let us think of a smaller example. All right. So suppose you had just 3 bits. Let us just say that if you had just 3 bits given to you as input. So let us just say that you have, if we take the first 3 bits or the most significant 3 bits, if we had this as your input, then it is not too difficult. Then you can say that the circuit is trivial. You just connect the bits. So this is your implementation. All right. So what you would get is 101 here. All right. If you just connect this by wires, these are your inputs. All right. You just connect this by wires and then you get the output. So you understand this is a trivial circuit, you can say, just for converting 3 bits of binary to 3 bits of BCD. Is that okay with everyone? Yeah?
Yes, sir.
Now, suppose you have one more bit. So let us say that you have one more bit. That is, we have, say, if we consider this much, 1011. So you have already seen, so 1011. So if it is just 1011, then you know that yeah, if it is 1011, then you know that this is the conversion, right? This is the conversion for 1011. Okay, so can we convert it? So let us see what we did. So what we did was, what you found is that you actually check that if this value, this is the value, right? This is the value. This is D3, right? So if you find any value greater than uh, 5, all right? So what is 5? So if you let us say that 5 is, this is the pattern, right? So if you have value greater than 5, so let us say that you just have a comparator. Okay, you have a comparator somehow. So this comparator, this is a 101 comparator. So if you have you put in, let me just uh, yeah, 5 is 101. This is 5. So let us say that if you have a comparator, so let us say that the job of this is to tell you whether the value is, so this is x0, x1, x2. So, and this is, say, z. So let us say that this works as z is equal to 1 if x2, x1, x0 is greater than or equal to 5, 0 otherwise. Okay. Of course, you can construct this. You can construct. Uh, so how could you construct it? So you take. Uh, actually, you would require not only three, but you would have four values. Really. So you have x3 also. So you can write x3. So you can actually make a truth table. Okay. So 0, 0, 0. So actually up to 5. So so let me just put it in a different ink. And so on. Say up to 1, 1, 1, 1. So here it will be all ones. Alright. Here it will be all ones. And here it's going to be all zeros. Isn't it? This is how this will work. So this is, you can say, x3, x2, x1, x0, and this is how this box is supposed to work. So you can think of how to construct this logic. So let us just say that you have this box. All right, you have this box. So what you can do is you can have a, so you know how to make an adder. So you have an adder. So let us say that um, you have this comparator. So you have these inputs, and it is going into this greater than or equal to 5 box. You have this output, and then you are just sending it to an adder. Okay, you are sending it to an adder. So let us say that you can. So what is it that you want to add? You want to add 3, right? So what you want to add is, you want to add 1. 3 is 0, 0, 1, 1. So you want to add 3. So basically you have your adder. Let us say that you have your adder. This is the usual symbol for an adder. You have an adder, and to that you want to add, you have this 4 lines. These are the same 4 lines which you had there. These are the same 4 lines which you had. So you can just, these are the same 4 lines. Maybe you can show that there's a connection here. All right. And then you want to add 3 conditionally. So how do you add 3 conditionally? So you can have, so these are obviously going to be 0, and you can have 2 AND gates. Okay. You can have 2 AND gates. This coming here, this coming here. So as you can see, this will, you can think of this as a module. This is, so you can say y. So this is, you can say that, you can say y is equal to and if you say that this is x, so we can just call it y. So you can say that this will, what will this compute? It will compute y is equal to x if if x is less than or equal to 5, or x plus 3 otherwise, right? So this is what this is doing. This is what this is doing. Okay, this is how you get y. So what you can do is, you can, let us say that you have this box. So you are just going to connect this box here, and you are well, you are, let us say, this is 0. All right, this is 0, and this result you are going to put here. This result you are going to get here. This result you are going to get here, and this bit you are going to get from, this is the fourth bit. So let me just put this in blue, just to indicate that this is not the input bit. This is 0, and this is your, this is the fourth bit, that is 1. So in fact over here, this is exactly what you will get. If you put this is exactly what you will get. Alright, this is exactly what you will get. So what you can see is that if you make a cascade of these units, this is so this unit does allow you to you to convert. This unit does allow you to convert four bits of binary to 5 bits of to 2 BCD digits. So the extra ones here, you know that this will be, you can say, these will be zeros. These will be zeros. Okay, so these will be zeros. So this is what you get. This is the result. This is the circuit for converting 4 bits of binary to 2 BCD digits. So you can, uh, uh, see how. So this is, of course, this unit. This is this unit. So now you can see that if you want to convert one more digit, you can augment this. So you have a cascade of these units to convert from binary to BCD combinationally. So this is, you can say there's a combination of. All right. So you can take it as an exercise to you know convert, let us say, 8 bits of binary to BCD. You can take this as an exercise. Of course, we'll put up this exercise, but you can take this as an exercise. So you can, so of course we have not shown you the implementation of this box, but you can implement this box as well. All right. So and make a module out of this. So you have seen how to make such. So this is one component. This is one component, and this is another component. All right. So you can design such components and connect them to make this circuit. Okay, so I think we can stop here today. Thank you.